demonstrate this. Okay, and this one can be explained by this. In the time domain, that is the integral of two time functions, f and g. F and g are two different time functions, and the integral is conducted in such a way, kind of look weird. For the function is ft minus tau, and here integral over g tau, and the tau is the integral variables here. Okay. Why we have to do this kind of weird things? This basically is called the convolutional integral. It has a special meaning in physical systems, and later on in one section later on, I will show you some movies to see why we have this one. Okay, but as long as in the time domain we have the integral of two different time functions in such a way, then its corresponding Fourier series transform, the Laplace transform will be very simple. It simply is the algebraic multiplication of the f and g in the S domain. That's it. Okay, so this is a very perfect, to me, is a very good properties. That means in the S domain we have a multiplication of the two functions. Then in the time domain we simply do the combination of the integral like this one. And this we can demonstrate with exercise of the example like this. Okay, so for example, we want to determine the Laplace inverse of this function. So basically, we can rewrite into the good one. So this is the time domain. Okay, so this is the time domain, and this is the S domain. In the time domain, we have for the convolutional integral, we have described by this. The multiplication of the two functions, its corresponding is ft minus tau and g tau and d tau. Okay, so maybe in this way I need to write it up two additional on the top. So ft corresponding is f of s, and gt corresponding is g of s. Okay, so we have such a definition that we do this one. So for this case, is there any way we can utilize the table? Seems not. From the tables I provide to you, seems we wouldn't be able to match anything given to this form, right? Of course, you can say, hey, can we do the factorize the things? So maybe in this way you can see, can we do the factorize, say, s and s minus 4 and then s minus 4 square. So this is ABC. Yes, you can do this one because we just learned this technique. Determine ABC, then you factorize and then do the same. Okay, this is okay. This is the okay method. Okay. And on the other side, I want to demonstrate to you using this technique. So maybe you can utilize this, and you can say we can visualize the two function basically is equal to 1 over s multiplied with 1 s minus 4 squared. So here we try to utilize the convolutional integral to see how can we solve for this one here. Will be okay? So to recognize that's a multiplication of the two things, and then here we simply do a little bit rearrangement. So for 1 of s, we know that is corresponding f of s is in the time domain equal to 1. And that is, we pick up this information here. Okay, and then for s minus 4 squared. This one basically is equivalent to 1 over s, and we do the replacement s minus 4 squared. Okay, so with this one, then you can easily see that would be into this pattern, this one here. Okay, we adopt that one. So that corresponding will be equal to E40 times t. Good? Any questions about this?
Do we need to scale it? But in factorial?
Yeah, 1 over s squared corresponding is t. And that one we don't need any scaling.
Oh,
You
yeah.
look at this one carefully. Right? Okay. So right now become very easy. Right now, in this way, we have these things prepared. So we apply the convolutional integral. So this one corresponding will be equal to, right now our f, this is our f, so that is 1. And this is our g. So that will be equal to E 4 tau and tau d tau. Good? Okay, so this one, if you implement this one a little bit, a few more steps, that one will be equal to 1/4 t e to the 4t and minus 1/16 e 4t and plus 1 over 16. Okay, so let me ignore a few steps of the, you have to do the partial integral a little bit, but that's the result here. Good? Okay, so this is a simple exercise for this.